Okay, so we're back after the break. The typo has been fixed. So we know how expectation values.
Close the.
Okay, yeah, choose. Work. This is all standard, so I'm not gonna stay here for too long. I hope there are no more typos. Why we need those things? Well, ultimately, the theory predicts probabilities. Well, let's call a sample space the set of all these eigenvalues, and they are understood as possible outcomes of their measurement that is modeled by the self-adjoint operator A, and the probabilities of the outcome being achieved, given that the system is in a given state, is given by the Born rule, which is just this thing. Well, yeah. This will the fact that this will be a probability distribution relies on the normalization of the vectors of the states, and you can also see here that these numbers, they won't depend on the phase, so it's sort of all it's coherent in a way. So we can see directly that the sum of probabilities is 1 exactly when the norm of the vector is 1, and so this last formula here is how I like to see probability distribution. So X is a subset of the possible outcomes, which can be understood as a proposition about the system. So the system is in the outcome of this experiment experiment is in this set. This is the question, and then there is a probability of this of the answer to this question being yes, and it's given by a sum of these probabilities, and it's going to be between 0 and 1. So a probability distribution can be seen as as a measure in a way, so a map that assigns numbers between 0 and 1 to subsets. Okay, is that fine? Cool. So what are the problems with this? There are a few. First one is that the pure states do not allow for the description of probabilistic mixtures. So mathematically speaking, the set of pure states is not convex, which I think is a good point. It is problem. We would like to be able to describe states connected to situations where we are just not sure which state it's being prepared in. So it would be good to have a notion of a state that's capable of doing this. And maybe more serious, another issue is that many physically reasonable observables, also those that are just used in the models, they cannot be modeled as bounded operators with spanning countable sets of eigenvectors. This is just too restrictive. So in particular, any continuous sample spaces are not available. Like you cannot even measure position in this setup, because you can treat it as an unbounded operator. That's fine, but I will argue that it is easier and more reasonable to speak about positive operator valued measures. So these are the problems, and the solution to the first one is basically to consider density operators, and to the second one to consider POVMs as observables.
Okay, but those things will not solve the problem that you mentioned earlier, that maybe some infinite dimensional such self-adjoint operators may not have any eigenvalues.
Yes.
Or sorry, any eigenvectors. So
you will see. So let's postpone this question.
Okay, so that
if
is
it yes,
taken care right now.
I think yes, it can be taken care of with the notion of a positive operator valued measure.
Okay.
You don't need the actual eigenvectors, you only need projections.
Yes, because here you have also defined the probability set to be corresponding to the eigenvalues.
Yes.
So
yeah, and we should be able to go beyond this, because the set of eigenvalues can only be finite, countable, because the Hilbert spaces are separable. and it's supposed to be the basis. But when you want to measure like position, which is just a continuous variable, then this is not gonna work. There are solutions. So let me go to this. So now the grown-up version of quantum mechanics. So the first realization is that instead of speaking about pure states, we can speak about one-dimensional projections, which they are also independent of the phase. And then we notice that instead of writing expectation values in the standard form, they are the same as taking the trace with an operator and this projection. And now we can consider a weighted sum of these projections. Now we add the states, but not as vectors in the Hilbert space. That would be taking superposition of states. We add the projections that the pure states define. And this way, this kind of matrix, operator, it reproduces the probabilistic mixture of pure states as seen in this formula. So here is a specific example because we take the projections to be the spaces spanned by the eigenvectors, because this is then clearly seen. So the conclusion from this is that ρ defined this way fairly represent the probabilistic mixture of pure states given by this probabilities Pn. So the idea is that this is a better, more general notion of a state, because you can always say that there's only one Pn that is non-zero and then it's one and you're back. But maybe this is a better notion of a state. And some more realizations are that the trace of such a thing is just the sum of these probabilities. So it should be 1 to make sense of the interpretation, and these probabilities, these numbers Pn, they should be positive, which is equivalent to this operator being positive in the sense defined before. And now an important point is that we can do, there is a converse to all this. So when you have a positive operator that has trace 1, you can always diagonalize it and write it as in this form. So any positive operator of trace 1 represents a convex combination of pure states. So that's a definition of a density operator. It's positive and it has trace 1. And in the grown-up version of quantum mechanics, we define states to be density operators, denoted like this. So they have trace 1, so they are, in particular, their trace class. They have finite trace. So it's a subspace of the space of trace class operators. So this fixes the first problem. This is a convex set. Okay, this I was not sure where to put this slide, but it has to be somewhere. So since we know what are trace class operators, there's an important property of this set. So first of all, you can put a norm on the set of trace class operators, which is defined by this thing. So I didn't tell you how to take a square root of an operator, but let's not go there. Just believe me, this makes sense. It's possible and defines a norm, and this space of trace class operators is complete in this norm, so it's a Banach space. And now we can consider continuous linear functionals on a Banach space, so this the dual space. And it turns out, perhaps surprisingly, that any continuous linear functional is going to be of this form. It's just taking trace with a specific bounded self-adjoint operator. Bounded operator. So A is a bounded operator on the same Hilbert space, and it's easy to see that when you take a trace with such A, it will define a continuous linear functional, but it is a surprising fact that this is the only thing that can happen. So any continuous linear functional will be given by some bounded operator.
What
Yes.
do you mean by continuous here? What changed?
Yes.
Sorry.
Yeah, fine. There is one more chair there. We are discussing trace class operators. So what I mean by continuity is that, so this is a map to complex numbers. Complex numbers are Banach space themselves, so we can speak about convergence there. So the continuity means that when you have a sequence of trace class operators, that is a Cauchy sequence, and you take the values of your operator. If the Cauchy sequence, if the sequence converges, then the values will converge as well. The standard sort of notion of continuity.
This Hilbert space is still separable, or no?
Yes. Well, so you can speak about trace class operators in more general, but I won't need non-separable Hilbert spaces. So we can. This makes sense more generally.
They are
but
countable. I mean, not continuous in the sense that like the vectors are like.
What is countable?
I mean, like not in the sense that the number of bases. I mean,
basis vectors. Yes.
Basis vectors. It is countable.
Yes.
It could be infinite, but it is not like continuous in the sense that it is. How should I say?
No, that makes sense.
Infinite in the uncountable sense.
Yes, but I don't think this is relevant in here.
In here, okay.
Yeah.
Okay, so it is continuous just because it is mapping to some set, which is.
So, well, to speak about continuity, so this is a function. This phi is a function between metric spaces. This is how you should see this.
Okay.
So if you have a map between metric spaces, you can check if it's continuous or not. So if it's continuous, if it preserves the limits of converging sequences.
Okay.
So you can do this in C, in complex numbers, and you can do it in trace class because it's a Banach space, if you believe me. And then it's a class. So not every linear functional will be continuous, but some are, and those are precisely given by self-adjoint operators on the trace. Okay. So this dual space, so the space of these functionals, is denoted with the star up there, and it is also a Banach space. So we can put a norm on this dual space. A norm of a functional is given by this formula, and this is general. So whenever you have a Banach space, you have the dual Banach space, like always. And in this case, this just works like that. And this correspondence that the continuous linear functionals are given by bounded operators, it also preserves the norm. So the norm of this functional is exactly the norm of the bounded operator that is associated to it. And therefore, we have an isomorphism of Banach spaces, of these two Banach spaces. So the one on the left is the dual space to the trace class operators, and the one on the right is the Banach space of the bounded operators. And this is my favorite example of a thing that you cannot see in finite dimension, because the dual of the space is the same thing if it's a finite dimension, but it's not the case here. So there is a precise sense in infinite dimensional quantum mechanics in which the operators are dual to the states, because states live in the trace class space, but not vice versa. There is this asymmetry here between states and effects will be introduced in a minute, but they live they are bounded operators of some sort, and this duality works one way but not the other. And some people think it's important, some people think it should be skipped. There are different intuitions about this, but certainly it's a fact that disappears in finite dimension. And I think this is important. So when I will be speaking about GPTs, I will want to have this sort of duality preserved. I will speak about states as primary, and then effects as living in the dual space. Yes.
Can you say again how this asymmetry appears? Because I think.
So it is true that the dual space of the space of the Banach space of trace class operators on a separable Hilbert space, it is isomorphic to the bounded operators, because any such functional is given by the trace with something. But it is not true that when you want to consider continuous linear functionals on B of H, they will be given by the trace with the trace. This is not true. There is more in there than just the trace class.
I see. Okay, thanks.
We'll go back to these things in a minute. Okay, cool. Okay, so now we also want to speak about maps between spaces of algebras of bounded operators. They can be unital, so if they take, we only consider linear maps and bounded maps, and they can be, they are called unital if they take identities to identities. Positive if they take positive operators to positive operators. Normal, this is a slightly more technical thing. So whenever you have a family of projections, you can sum them, and this equation has to be satisfied for any such family. So this is maybe I don't think I understand it too well. It's a technical condition, but you will see in a minute why this is useful. Completely positive, so yeah, quantum information stuff, you know this, so it has to be positive, and also all the maps that are extensions, so you just put on the side another quantum system that's finite dimensional and extended the map by identity, and this map is not necessarily positive if f is positive, so it's a separate requirement to demand that all these maps, they're also positive. Quantum channel is a map that satisfies all these properties, so it's unital, completely positive, and normal. And the last thing that is useful for me is the unitary, the notion of a unitary channel. So we can speak about unitary maps between Hilbert spaces, and then a channel is unitary if it works like this. So you take operator with the sandwiches this, and then you get an operator on different Hilbert space. So usually unitary operators are defined in a single Hilbert space, but there's no problem in generalizing this definition to maps that go between different Hilbert spaces. It's just the same thing. So U star U is identity on one space, and when you switch them, it's the identity on the other space. Yes.
Normal maps are unital, right?
No.
Normal maps are unital.
Unital. No, I think they don't.
Some of
well,
EI will be identity, I guess.
It could be, but this is any family of projections. Wait, this is a good question. I think they will be unital, yes.
Okay.
Well, I'm not entirely sure. So I will check this, and let's talk on Tuesday. Because usually it's stated as a separate condition. So
yes,
we need.
but I mean, if you think of this projection of vertex as like the complete bit, I mean,
Yes.
this affects as like some.
If they sum to
decomposition of
identity,
then
yes.
in that sense it would
But
mean.
you don't
But then
know if
you don't know
f on E is still
So this means.
an eigenvector on yes.
So it has nothing to do with eigenvectors. But let's say we
Okay.
have identity written as a sum of the basis projections, right?
Yes.
Because now its identity is as a bounded operator. So we can choose a basis and then consider a sum of projections onto the basic vectors. And so this has to be satisfied. So if this is identity, then it has to be a sum of the images of these projections. But you don't know if the image,
each
if
of
this
these
is
are
the
like,
basis. So
still
it doesn't have to
projections
be.
or not,
Yeah.
like orthonormal projections or not. Okay.
Yes, I think it's not true.
Yeah.
It doesn't. So unitality does not follow from normality.
Okay.
Yeah. Very good question. Thank you. Okay. So why this normality is important is. So I told you that this is not. The symmetry is broken, so you cannot. You can speak about. Maybe put it differently. You can speak about. You can think about states as being functionals on bounded operators by just taking the trace, and this will be positive, continuous, linear, positive functionals, and they will be normal. So they can be states can be characterized by as being those functionals on the space of bounded operators that are not only linear and continuous, but they are also positive and normal. And then why we care about normal maps is because when I have a normal map, then I can precompose, if I see my state as being this functional, I can precompose it with f, and this is again going to be a normal map because normal maps compose. And only if the map is normal, I have this other map that goes the other direction, so to say, and it takes states to states. And this is called a predual map because we've seen that the states live in the predual space because the dual is the bounded. Does that make sense? Or it's too quick? I can say it again, or maybe you have questions.
You could repeat it.
Yes, of course. So let's say so states are density operators. So they have trace 1, they're positive. And we can consider linear functionals that they give rise to on the space of bounded operators by just taking trace. Fine. They turn out to be linear, of course, because trace is linear, and positive because the states are positive, unital because states have trace 1. So when you take A to be 1, then you take a trace, and trace is 1, so it takes 1 to 1. And it turns out that they are characterized by this normality condition. So any functional that has all these properties and is also normal is given by a specific density operator. It's now a subset of all of those. So and then why we care about normal maps between algebras of operators is because we can use them to map states to states. Because, well, maybe I can draw it somewhere.
But
so
these positive normal maps will also map the self-adjoint operators to self-adjoint operators, right? I mean, like
they map positive to positive. And positive operators, they are self-adjoint.
Oh, yeah. But okay, so now you show that for the states, like the state, the set of states will also.
I think it may be useful to draw one thing, so I will try to do this. I have no idea if it's going to be visible on the recording, but let's hope so.
But I guess you can write on that itself. On
This
screen.
on this.
Yeah.
Triangle,
On this
yeah.
screen, yeah.
But can I display at the same time, or?
Yes, I mean,
Yes.
everything
Okay.
will be recorded, I guess.
And you can also save this.
Yeah.
This thing you write, I think so. Nice, I think so.
Do you know how to?
No. Yeah. Yeah.
Okay, amazing. So we have this map, and now if I have a state on the second Hilbert space, I can see it as a map of this form. So it goes to the complex numbers. This is this phi rho, and now rho is state on the second Hilbert space. And now if this map is normal, so it preserves this families of projections, well, this does, because this is a state, then the composition, so this thing also is a normal linear blah blah map. So this thing defines a state now on this Hilbert space. So you can see this composition as something that takes states on here to states in here, and this is precisely the condition that needs to be satisfied for a map between algebras to give rise to the predual map on the states. Right, because when you compose this with this, you have a map from here to there, which satisfies all the properties, so it is a state. And this is how this thing is interpreted as a state. Everything relies on this realization, which is a non-trivial theorem, that states are precisely these unital positive normal functionals. Okay?
Okay.
Yeah, well, you understand. Well, so when you see this first time, it's yeah, it can be very confusing, and probably I'm not explaining it too well.
Don't say.
No, don't say this.
Okay.
No, also don't say it because then you will think it will weird. Yeah.
Okay. Is this disturbing? Maybe.
Don't say.
Okay. All right. So that's the notion of a gradual map. So whenever, just to maybe sum up, when we need all these properties. We don't need complete positivity, but we need unitality, positivity, and normality of a map in order to define the gradual map that will map states to states. Because, well, conceptually, this maybe makes more sense to speak of channels as maps that, they take states to states and not like just operators. Why? So the correspondence works precisely if this maps between algebras, they satisfy this extra continuity property with families of projections. Okay. Okay, spectral theorem. So now we're moving the direction of POVM. So we want to understand how to maybe better understand the probabilistic content of a self-adjoint operator treated as an observable and then generalize it. So the way to do this, if you have a bounded self-adjoint operator, there is a compact subset of the real line, which is the spectrum, and the projection valued measure. So a map that takes now sigma is just a subset of R, so it's also a topological space. It's compact, and this F here means that we take in this case this will be Borel subsets. So the point is that we need a sigma algebra. Do you know about sigma algebras and some probability theory? Not everyone. Well, okay. So it's a family of subsets. So some subsets can be taken. So the idea of this thing is that this is a project. I will speak a little bit more about this, but let's not stop here. So I can take this is just a subset of a real line, and you can take a smaller subset, and to many of such smaller subsets, this machine that is called projection valued measure, and this is uniquely associated with any self-adjoint operator. This is like a theorem that says this, that constructs this, that there is such a map that takes subsets to projections. Well, this is why I use P of A. And it has this property that the operator can be written as this integral. And this integral is generalizing the previous notion where we had a sum over the eigenvalues and the corresponding projections into the spaces spanned by the eigenvectors. So you can make sense of this idea in more generality, even if, so that's your question, I think, even if there is the sample space is not just discrete. Yeah. So in fact it works, but you have to change the notions that you use and speak about this projection valued measures. But you can do this and it works, it's nice, and it has this property that whenever you have a state, you can define a probability distribution. So now to each subset of sigma, you assign probabilities by, this is again the Born rule, but in a more general sense. Because before we had these projections into the spaces spanned by the eigenvectors, right? And now we can forget about the eigenvectors, but only use this projection valued measure. And because states are again normalized properly and everything, this actually defines a measure. And now interpretation is the same as before. So the subsets of this sample space, which can now be continuous, but it is still bounded, represents propositions about the system that are measured with this specific self-adjoint operator, and these numbers are probabilities that these propositions are true given the state rho. So here we take care of like both these problems in a way, because we treat instead of taking expectation values, we take trace with an actual state, with a density operator, and we don't need countable sample spaces. We use the spectrum of the operator, which is given by a theorem. So this this is maybe not very easy when you see this first time, but we don't have to understand this in detail, because we want to generalize this. And I think so. Sometimes it happens that when you consider more general things, they are actually simpler, because you care only about the relevant structure. Well, that's at least my hope and part of my experience. So now the idea is that what this operator does in terms of probability, the probabilistic content of quantum mechanics. It is a machine that if I fix my operator, it gives me the spectrum, and whenever I specify what's the state of my system, there is a procedure to give me the probability distribution over the spectrum space. So in a way, this perspective on a self-adjoint operator as an observable, it is a machine that takes states and gives as an output probability distributions. Does that make sense?
Can I ask?
Yes.
So these are projection operators. So it's like having yes/no questions, or they are more general.
No, these are projections.
So
they will also commute.
That's why they represent propositions, right?
I think the interpretation holds more generally. So let me, because this is exactly what I'm gonna drop now.
Okay.
So now I want to consider a similar thing, but okay. So the definition: positive operator valid measure. Yes. Here or before?
Before here. So what guarantees that these probabilities will be of this form, this trace of rho px?
No, this is a definition of a map. So when I have such a thing, this P, I can define this object, and it turns out that it will always, it generalizes what we had before, and it will always give me probability distribution if rho is a state.
Yes, I understand. But now the question is whether this. So this is one such definition, one such possibility which could define a probability distribution.
Yes. And you want to know? Okay, very good question. I will go back to this. So it's actually, there is a sense in which not this, but the more general notion that's on the next slide is the unique solution to this problem. So what? I want an observable to be something of this form. So now I drop this condition that this. I want a sample space. Now anything, it doesn't have to. So I don't think about operators anymore. So this sigma is just some space, and I define an algebra of subsets, and to any subset in this algebra, I assign a bounded operator, and I want this map to make sense as an observable. So I want this construction from the previous slide to give me a probability measure. So whatever this is, if I have such a thing, it is a procedure of assigning probability distributions to quantum states. And it is the most general such procedure if I want, so because we've seen this duality, and if I want to treat it as a map that takes states to probability distribution, I will go back to this in more detail later, but if I want this to be such a map, and I want it to be continuous, then it needs to be actually of this form. So there is no more general way to do this, unless you want to sacrifice the continuity.
Okay, but okay, so another question.
So not okay.
Yeah, not related to this, but I mean, what is the point of generalizing this set sigma to some arbitrary subset? Like, I mean, is it still the subset of the real numbers?
No.
Or?
So that's the point. So next week, sigma is going to be a group.
Okay.
It can be a manifold. It can be whatever you want, basically speaking. So it gives a lot of flexibility to the framework, because I don't think it's I don't think it's general enough to just think that you always measure like real numbers. I mean, it can be more structured there, and so yeah, I think it makes sense. I will also speak about probability theory in some more detail later on, and so I think it is a very useful generalization in this sense. And also there is a way to go back. So if there is a converse theorem, so if the sigma is actually a compact subset of the real line, and all this we call them effects, these operators that are in the image of the POVM, if they are all projections, and if they all commute with each other, then there is an operator, self-adjoint operator, for which this is the spectral measure.
Okay.
So this is a strict generalization of a notion of an observable that is given by a self-adjoint operator, and it gives a lot of flexibility that is useful in the framework. So I can do nothing in my framework without the POVMs. Like everything is based on this thing. So if you don't like it, then that's fine. So in order to satisfy this, so I want this PE row to be a probability distribution, then it gives some constraints on how this POVM, the map here, has to have some properties, and this is what follows. So E of sigma should be the identity in order for the probability on the whole space to be 1, and all these operators, they are effects, which means that they are bounded operators, of course, but they also have to be bounded by 1. And this should be 1, not like bound. Well, these are numbers. No. Okay, sorry. No. So there is the unit interval in the space of operators. We have order in this space. Let's. Okay, maybe I should talk about this. Wait, give me 1 second. Okay, yeah, I can say a little bit. Sorry, I missed that there is an actual issue here. So in the space of bounded operators, we have order, because we know what does it mean for an operator to be positive, and then we can subtract one operator from another and check if it's positive, and if it is, then one is greater than the other. So this is what this order here refers to. So effects are operators that are smaller than an identity in this specific sense, and bigger than the zero operator in this sense. It's not super important, but this is how it works. There is a subset of bounded operators that we call effects, and they satisfy this property, and this property has to be satisfied for this assignment to be a probability measure. Otherwise it won't work, because basically the probabilities will be too big. This is straightforward when you write everything down, but let's not do this. And another property it has to satisfy is that when you have these two subsets that are disjoint, then the resulting effect is just the sum. And if this, and it's one way and the other. So if this is satisfied, then it's a POVM. And if this sort of thing is supposed to give rise to probability distributions, it has to satisfy these things. It's quite abstract, perhaps when you see this first time again, but when you think about it, it's actually quite nice and conceptually pleasing, I would say. More questions?
I think maybe I missed something from what you were saying.
Yeah.
This last property is for
Yes.
all the POVMs or the effect?
So POVM gives a map. It's a map from subsets to bounded operators. So if you have two subsets that are disjoint, you can take the union, and it's again an element of your sigma algebra. So there should be a corresponding effect,
But the okay.
right? And it has to be this one for everything else to make sense. Otherwise, the probabilities they won't sum properly, because x is a proposition and y is another proposition, and if they don't overlap, then the probability of this being true and this being true, it should be a sum of probabilities. So this is assured by this condition. And the previous one is necessary for the probabilities to be between 0 and 1. Yeah, there's no magic, there's just some notation and stuff.
Right. Okay. Thanks.
No worries. We can also stare at this a minute if you need this.
If they are not disjoint, x and y,
Yes.
but you can still write it like some sets which are disjoint, like taking the overlap on the
Yes.
and then also this effects will be like.
So I think not always you can have the wait. Very good question. Give me one second. Yes, so I think what's gonna happen, and we're gonna see this later on with probability distributions, is that when you take when you drop this condition of disjointness, then you will have to have another term here.
Yes.
You have to subtract the intersection that you
intersection.
just counted twice.
Yeah.
I think this should work. Yeah. So later on there will be more structure on sigma. So it's because for now it's just a set, and we specify this algebra of subsets. But later on, this is gonna be a group or some homogeneous space. So it's gonna be a topological space, and there will be more structure to play with, to put restriction on these things. And then I'm not sure when some things are gonna break, but this what I've written, I checked, and it certainly makes sense in this generality. What's later? Okay, on the next slide I have an example, so maybe this is gonna be helpful. So position observable. So yeah, we would like to be able to measure position of particles, and so you can already see that if position is just if it can be anywhere your particle, then this space of outcomes is continuous and it's not compact. So it cannot be just described by a single self-adjoint operator, bounded self-adjoint operator. So one way to do this is to drop the boundedness requirement and define the unbounded operator of position. That's what people do. But another way is to speak about POVMs. And so there's a very simple construction to define a POVM that will measure position. So the Hilbert space is the square integrable functions on R with the Lebesgue measure, and there is this operator. So well, the sample space is the real line. It's a topological space. We take the Borel subsets as our sigma algebra, which is the smallest sigma algebra that contains all the open sets. So I can ask the question: is my particle in this open set for an open set? But I generate the smallest sigma algebra out of these sets, and then for any such set, I can define this multiplication operator. So I have a multiplication function which is integrable, the characteristic function, which is integrable. So the characteristic function is just 1 on a subset and 0 everywhere else. It's not continuous or anything, but it's integrable and square integrable. It defines an operator on the space of square integrable functions. This is how it works. It's just written here. Chi is just the function that is 0 whenever x is not in y. So it cuts, if you think about the psi as being the wave function, if you multiply it with a characteristic function, it cuts it in a way. I can maybe do it. So if let's say okay. So let's say this is R, and I have my wave function, and let's say I've chosen this is Y, this is my subset. When I multiply psi by the characteristic function, this is gonna look like this, and then it's gonna be this is Y, and then it's gonna be 0 here and there. Because this thing is gonna vanish whenever x is not in Y. So whenever you're here, this thing is 0, and when you're in Y, this is 1, so you get what you started with. And then what happens is what we want. So probability of measuring position of a particle in pure state in the subset Y is given by this integral. So when you apply the definition of like how to get probabilities out of a POVM, this is a POVM, and it gives you precisely the probabilities that you want. So you integrate the square of the wave function over the given subset.
So are these projections?
Yes, these are projections. So when a POVM it has only projections as effects, we call it sharp. It's a sharp POV. So this is not the most general example, but this is something relatively simple that already, is. We need to speak about this thing. Well, that's one of we cannot just deal with bounded self-adjoint operators to do this. Okay, is this convincing that this works? Okay. Yeah.
Yes, but this expectation value is of m chi y, right? So, yeah, here.
Yes, you're right. I mean, it's sort of the same thing if you understand it as a function. So but yes, you're right. And there should be m for coherence. So normally, well, on the previous slide, you should take trace, right? But now rho is a pure state, so you just take the expectation value, and this is just multiplication. This Ex is just multiplication, so you get this formula.
Okay, so this looks very much like the eigenvalue equation, right? But it is rather than a number, it is just a function. I mean,
yes.
In that sense, like this characteristic function.
Yes. So that's the point. So there is a way to make sense of all these things. So you just need to sort of change the perspective a little bit and not stick to this eigenvector and eigenvalue stuff, because it's just not general enough. All right. Anything else? Okay, we're almost out of time. Oh, this I already said. Okay, perfect. So that's the last slide for today. And this is basically all I need to speak about the framework of quantum reference frames. So there are different notions of different topologies that one can consider on the space of bounded operators. There's many of them. They are related in complicated ways, but the only one I will need, besides the one that comes from the fact that P of H is a Banach space that we talked about, is this sort of ultra-weak topology, which is defined by just saying the following. I call them operational topologies because I want the things, so like operators or states, sequences of those things, to converge whenever the expectation values that they give rise to, so like complex numbers that can arise as probabilities, if those complex numbers converge. So in a way, this is the notion of convergence that is that comes from the probabilistic interpretation of the framework. So when I have a sequence of operators, I say they converge ultra-weakly to some other operator if for any state that when you evaluate the state on the sequence, you have a sequence of numbers, and then you can take a limit in the space of complex numbers, and if this is the same thing as just evaluating rho on some specific operator, then I say that AN converges to A ultra weakly. This is the terminology that's just like 50 years old, and we have to stick with this. It's ultra weak because it's weaker than some other topology that was weak and stuff. And on the space of states, we do the same thing. So I say a sequence converges, or states converges, if for any now bounded operator that is fixed, the expectation values, they converge. And this, I don't think, has been defined before, and we call it operational topology on the space of states. Okay, so this does that make sense? One of the ways to speak about topology is just saying what converges.
But we want both of them to happen. Like
Both of the, so the first one is the topology on the space of bounded operators, and the second one is topology on the space of on the state space. Yes, and I treat them very differently because I care about this duality. So it is a fact that trace class operators are bounded operators, but conceptually they are very different because the bounded operators they live in the dual space from this perspective. So they are really different sets. And I care about convergence differently in these things. Like it's a sort of like dual thing, right? You can see, it's just dual. Right. Did they kill you today? You are alive, Sina? I think it's gonna get more exciting next time. But that was really necessary to, and if something is unclear, then feel free to come. I'm usually in the room 222 here, and I can send you the slides and also my thesis. I sent it already. I think it's so there is an appendix where all this is done, as well with some more commentary.
It's going to be more. Is going to be more understandable because we're going into the midlife crisis, right?
Yeah, so the midlife crisis is this GPT kind of setup. So we want to, this is not necessary. So the framework I'm working on is about quantum reference frames. So it's about quantum theory. It's not more general. But I'm pretty sure I can put it into the more general setup, and I'm working on it, and I think it is instructive and interesting to see how quantum theory fits into this more general landscape. So I will probably like to start, since I've done all these slides, I will probably like to start with this next week. Because I think also the perspective on observables is cleaner, and the channels, like you drop this unnecessary Hilbert space structure, and then everything is nice. That's my view on the things. But if you're not, if no one is interested, then we can just skip it and go for quantum reference frames as well. So just feel free to ask for this. All right, thank you for coming.
Thank you.
I stop the recording.